we're now going to prove these two trigonometric identities. Strictly speaking, this proof should be in a pre-calculus course, but these identities are so important, I think you should see this proof at least once. Maybe you've seen the formulas, but have never seen a real proof of them. So the proof is kind of nice, so let's take a look at it. Let's actually focus on just the first one. The sine of y plus x is equal to cosine, sine, cosine, sine. Now, I have, when I used to teach pre-calculus, I had a silly way of remembering that. I always got these confused, and they're so important you should somehow fix them in your mind. So I used to say, well, sine. For some reason I was thinking cops, silly. So silly over here, if you put them in the right order, it's silly cops, SC, silly cops, plan, that's a plus, silly capers. So that's one way, kind of a crazy way of remembering them. And then the other one, if you look at this one, well, we had silly cops. Now let's have crabby cops. So here it's crabby cops plan, or no, here it is. Crabby cops make sour sergeants. Crabby cops make. So the M is the minus. Up here it's silly cops plan silly capers. So there's the silly formula and the crabby formula. There's kind of similar. You need some way of keeping them straight in your mind, and that's how I used to keep them straight. Maybe you have a better way. But let's look at the first one. Let's prove this first one. And we're going to do that by looking at this diagram down here. Here's x, and here's y. And so the angle x plus y starts down here at the line AB and goes all the way up here to the line AD. So we want to, first of all, see in this diagram what the sine of x plus y should be. And here's the formula for it. And let's take a look at figure 2 in order to see why that's the case. We drop a line from D down to the baseline AB, and the point where it intersects we'll call it G, and that's a perpendicular. So this little thing in here is a perpendicular line. So let's see if we can, I could put a little box in there to remind us that that is a perpendicular angle there. And also up here where C is, we draw a parallel line over to hit the other red line, and that would make that a perpendicular angle also. We'll put a little box in there to remind ourselves of that. Alright, so that's our construction, and then with that construction it's pretty clear that the sine of x plus y is this side here, this red side, D to G, divided by D to A. That's the hypotenuse of one of the right triangles in this picture. Now let's get rid of our little helpers there. This angle x, we're now going to see that it appears in other places. See if you can anticipate one of the places where it's going to appear. There's another angle in here that's equal to x. And let me help you by doing figure 3. Actually, there are two places. This angle here is the same as this one because of a theorem from plane geometry, which says, I think they're called opposite interior angles. When you have a parallel line, you have parallel lines EC and AB, and a transverse line A to C, this angle up here, this x, and this x down here are called opposite interior angles, and there's a theorem which says they have to be equal. It's pretty clear from the picture that they are equal, at least numerically. And now this one up here, this x, is also equal to the other two, and the theorem for that is, what's it called? It's x is the complement of this angle down here. This angle down here is F. We'll call it F. And remember this thing over here this thing over here, this is a right angle. You know, it was, I didn't draw the little box in there because our picture is getting a little messy. But that's a right angle. So this angle down here is the complement of this angle up here. In other words, the two of them together add up to 90 degrees because all the angles in the triangle have to add up to 180, and this takes up 90 degrees. So this one and this one have to be what are they, complements of one another. For instance, if this were 30, then this would have to be 60 down here. But you can say the same thing about f and x over here. This is a right triangle too. You know, this one little piece here. Again, I didn't put the box in because our picture is getting kind of messy. That's a right triangle. And so, bad perpendicular marker there, but that's a right triangle. So x and f are complements also. So that means x and x, the two different x's, have to be the same. And in this case, you know, if this is 30, you'd say, well, this is 60, and so therefore this x has to be 30 also. So we have those three equal angles. And what do we do next? Well, let's go up and look at our formula here. The formula has four pieces. It has cosine, sine, and cosine, sine. Four pieces. And it also has a plus. Let me try to show you in the picture where those four pieces come from and where the plus comes from. So to do that, let's look at figure 4. All right, where's the plus come from? Well, remember, dg plays an important role in our calculation of the sine of x plus y. And dg is this line here. And dg can be broken up into two pieces, de and eg. And we'll see that this plus here in this formula eventually becomes this plus up here in this formula. Okay, so that's where the plus comes from, and we'll see the details of that in a second. Where do the four terms come from? Well, they come from these four equalities here. And how do you prove those equalities? Well, you just look at the picture and see that they fit. Let's just look at one. Let's look at this first one here. This DE equals a cosine of x over CD. So let's find DE in our picture. That would be this thing here, DE. And let's find CD. Well, CD would be this hypotenuse of this little, what is it, the triangle DEC. And clearly, if you divide through our formula by CD, you get the true expression d, or cosine of x equals DE over CD. So let me say that again. Let me clear my little helpers. The cosine of x, and we're looking at this x up here, the cosine of x is DE over CD. So that's surely clearly true. That's just a definition of cosine. And similarly, all the others can be proven. It's not really a proof. I mean, we've drawn our picture so that they're true. And you can check the picture against the formulas and see that they are true. Now, what about this one here? Well, that one, you know, we've already discussed. That one is, we break up the line DG into its two parts. And there's one other formula that we have to look at, and that's this one, EG equals BC. So we're saying that E to G is the same as B to C, and that's because we've drawn this red line up here parallel to GB. So we're talking about a parallelogram there, so the sides are actually more than a parallel. We're talking about a rectangle, so the sides are equal. And you know, the reason we need this is we want to get this triangle, the triangle ABC, into our calculations. And as we'll see when we start out, we don't have it in there. We have the piece EG in there, but then when we make the transformation EG to BC, that brings in that second, that lower triangle. So let's see how that all comes together now. So we'll start with our definition of sine of x plus y, and we just start substituting. DG is the two pieces. So, and recall that plus that we're looking at down here, this plus here is eventually going to become this plus up here. That's why there's a plus in the formula. All right, so let's go on and substitute some more. DE we can stick in there. And EG, where is EG? Okay, EG is here. This is, EG is this line from here, from this E down to G, and that's not related to anything directly. But if we go over here to CB or BC, which is the same thing, we're going to get that bottom triangle and all its pieces into our picture somehow. So that's why we do the EG to BC transformation. And now we can do this. BC is, we're bringing this x into the picture, really, at this point. Cosine of x is now part of our picture, I think. Or where is it? Sine of x, I guess. We brought in AC sine of x. I think that's what we brought in. All right, let's keep going here. What do we got? We got a CD, so let's make that substitution. And we got an AC. Let's make that substitution. So these are all substitutions that we are allowed to make because of really just definitions of cosine of y and sine of x, etc. Now look at this. We have an AD in one of these terms. We have an AD in the other term. And we have an AD in the denominator. The numerator is this whole sum here. It's a little hard to see, but that whole thing is a sum. Let me do this. Perhaps if we make it, put it into our A over B format, it might be a little clearer what's going on. Yes. Okay, so there we have a sum on top, and everything is divided by AD. But now watch what happens when I factor out that AD. So that's one of our ops. Let's factor all terms. Now we have an AD in the numerator and an AD in the denominator. They're going to cancel one another out. So I can just simplify my fraction. If I do that, I get the formula that I want. So we're done with the proof almost. The proof is not quite complete because this picture assumed certain things implicitly about x and y. It assumed that they're acute angles, that is, they're less than 90 degrees, and they're positive angles. That's implicit in the picture. And moreover, that they sum up to something less than 90 degrees, less than pi over 2. So we've really just proven our formula for a very special selection of angles. How do we prove it for the other angles? Look down here in our mimicking picture down at the bottom. That's a mimic, a replication of the diagram we're looking at up top. This one on the bottom, though, I can manipulate without any, I don't have to draw anything else. I can just change some values. In particular, I can change x and y. As I change x, my picture changes. Or as I change y, my picture changes. That way I can look at various types of x and y and kind of understand what our situation is. So there's the situation we've just proven our formula for. Let's look at another situation. Right before that, let me bring up my calculator here. Here are our 4 equalities that we used in our proof, the 4 plus 2. Those are all the equalities that we used in our proof. And this one over here says, yes, they're all true for this particular diagram. And in the background, I've actually come up with some numbers for A, B, C, D, etc. and plotted them here, and we can see that the angles are right angles and the picture looks right, and all these equalities are numerically confirmed. However, let's suppose that we change our angle. Suppose I look at a situation like this. Suppose what have I got here? I've got a negative x and a very big y, so my picture changes completely. Notice I lose some of my equalities over here. I lose these two. And you think, okay, well now I'm in trouble because I can't use that same sequence of substitutions that I used before because they're no longer true. But I can change these. Now the picture is different, so I have to look through my picture and change my formulas to correspond to my picture. And we can see why this one is no longer true, for instance. This is no longer true because AC and AD are positive numbers. They're always magnitudes. And the cosine of y in this case, look at y as this 2.26. If we look at the cosine of y, it's going to be a negative number. Here's the cosine of y. It's a negative number. So this formula as written cannot possibly be true. But we can make it true by just sticking a minus in there. And the same with this one. We can make it true by sticking a minus in there, and then we go through our same process of substitution, and you think, well, by putting minuses in there, maybe I'm not going to come out with the same formula up top. Maybe I'm not going to come out with this same formula. Maybe I'll come out with, I don't know, with a minus in the middle or a minus in front. Well, it turns out you don't. If you go through the process, you'll see that the two changes that you made cancel one another out, and you end up with the same formula. I'm going to do that for one case. Let's look at a couple of more cases just to see what the possibilities are. Let's look at this case here. All right, now in this one, we lost this equality. We also lost this equality, dg equals de plus eg. But we can change these formulas up here, this one here. We can look at our picture and make them right. And we can see why that formula is no longer true. If you look at dg, d is here, g is down here on the x-axis. That's the same as it was up here. G is on the x-axis. But now E is below G. E is down here. E is below G, whereas before E was above G. So our picture has changed, but we can fix our picture by putting a minus between the two. And now that's true, and we can fix this one by just putting a minus in there. And you say, oh, okay, then you go through your substitution just like you did before, and it turns out that these two changes will cancel one another. But let's look at one more. This is perhaps the most challenging one. Here's another picture, and we've lost some equalities there. In fact, we lost our main equality. The sine of x plus y is no longer equal to dg over AD. Ooh, now that seems strange, because if we look at dg, that's d up here, g down here, AD, it seems like that's always got to be true. But look at our new picture. Here's dg. I can go through that. D to g. Here's A to D. And in our formula, those are always positive numbers. Those are always magnitudes. So this up here cannot be true because the sine of x plus y is now negative, because x plus y is actually, if you look at what x plus y is, let's actually take a look at that. X plus y is going to be a negative number, I hope. Yes, it's a negative number, and the sign of a negative number has to be negative. So, that's why that equality up there no longer holds. But again, we can fix it. We can fix this one. Make that a minus. Now it's true. And this one we can fix. Make that a minus, and this is true. And you confirm these by just going down to the picture and seeing that these new formulas conform to the picture. And our other two, we've already made that minus change in there. So now all our formulas are right for this picture, and we're just going to start substituting like we did before. And you're thinking, well, I put some minuses in there in a couple of places. I've made things, put a minus in here. How do I know I'm going to come out at the same place? Well, you just do it, and you see that those changes all cancel out. So let's go through it one time. We're now going to substitute for dg. And let's get EG into the picture. And BC is this. So we're substituting just like we did before, and we're hoping all the changes we made cancel one another out, and we end up with the same formula that we did before. If we had to adjust our formula for different types of x's and y's, it would be a real nuisance. So we hope that we can get to the same place with the same process of substitution. So let's see if we do. Okay, this is where we see some cancellation. Notice I have a minus down here. There's a minus right there. A minus between our two formulas. We'd like to see a plus there. And look what happens when we put CD in there. CD now has a minus there. So when we put it in there, we end up with a plus. And now we do just what we did before. We can factor out the AD, and it cancels on the bottom. And we end up with our silly formula. This is our silly formula. It's silly, cops, plan, that's a plus, plan, silly, capers. So we're right back where we started from. All right, so let's now prove the second formula. Now we could prove that in the same way by drawing a picture like we have here and putting the pieces together. The picture would be a little different. It would look like this, and you would now be focusing on AG over AD. So you'd be focusing on this AG divided by AD. And you would set up your four equalities just as you did before and substitute away. But I'm going to do it a slightly different way, just to show you why we bothered with some of our simple identities for sine and cosine. So let's look at it like this. Here's our formula for the cosine of x plus y. Okay, and let's keep track of that 92781 at the bottom. I'm going to make some transformations to my formula, and I want to make sure I don't change that. If I do, I've made a mistake. So let's look at it up here. Let's put some more decimals there so it's the same. Okay, so watch this down here, and this up there, as I transform the formula in here. I hope I don't lose my initial value. So the first thing I'm going to do is we have a formula for sine of x plus y. Let's see if we can get sine into our picture. I recall one of my basic identities. If I change the cosine to a sine and put pi over 2 in there, I end up with the same value. That's one of our basic identities. And now I want to think of this inside here as two things. So I'm going to group the first two things together. And now we can use the formula that we just proved. The first term is now a little more complicated, but it's still just a number, and the second term is a number. So we can use our formula for sine that we just proved, and it should be in our This one here, we know that's true. So we get this. And notice our 92781 still have what we want down there. And let's get rid of our grouping. We no longer need our grouping. And now look at this thing here. We should know how to convert that to something else. Let me get rid of this. I don't need my... Let's just do a substitution. Now I recall that this is somehow related to the sine of x. And notice, ooh, test, this is it. You got it wrong. Well, this is the one that has the minus in it. So we knew one of them did, and it's got to be this one. Now we have the 1 down there, so that must be the correct formula. So let's replace that piece. And now we go over to this one. And let's replace this one. We know that that is related to the cosine. So let me bring up my replacer. And I'll put a cosine here. Cosine there. And I get rid of the 1/2 pi. And I see that I have the 1 down here that says that they are the same. So this is the one you don't need the minus. So let's do that one. And now notice I have a minus sign and a sign. Let's just do a simplify. And there we get our formula for our Krabby formula. Krabby Cops make, that's the minus, sour sergeants. And that was a lot easier than going through this picture here. But just as an exercise, you should try that. Stop the video and write down all these pieces and make the substitutions just as we did before, and you'll see that you end up with the second formula, that you end up with the cosine formula, just as we did for the sine formula. Alright, so that's it for these two identities. We're going to eventually use them to prove that the derivative of the sine is the cosine. And then we're going to combine that with some rules for differentiation that we develop, and we'll be able to show that the derivative of the cosine is minus the sine. So that will be 2 or 3 lectures down the road. But that's all for this.